Okay. A very good day to all my students over here. Welcome to the next part of the chapter, that is part 4, atomic structure. Today, I will try to complete the chapter. What I am going to begin with is the Bohr's atomic model. Okay. So, now let us begin the chapter, my dear students. Okay. Now, Bohr's atomic model. It is based upon the Planck's quantum theory. It is based upon the Planck's quantum theory. Okay. Now, let me discuss the postulates one by one. Number one. Number one. Electrons revolve around the nucleus in circular orbits having definite energies which are called as energy levels. Which are called as energy levels. Energy levels. Okay. Next one. The angular momentum of an electron in a given stationary state is given by a formula. The angular momentum of an electron, mvr. That is the formula of angular momentum, and it is given by nh by 2 pi, where n is equal to 1, 2, 3 and so on. And in this formula, m stands for mass of electron, mass of electron. V stands for velocity of electron, velocity of electron. R stands for radius of the orbit in which we find the electron, and H stands for the constant which is called Planck's constant. Okay. Please note over here that the angular momentum of electrons in atoms is quantized. That means the angular momentum of electrons in atoms is quantized. 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 It is always a whole number. That is the second postulate of the Bohr's atomic model. Next, number 3. Number 3. There is no loss or gain of electrons as long as it moves in a given energy level. As long as the electron moves in a given energy level, okay, if there is an electron, there is a nucleus say, and there is an orbital, as long as an electron is there in a given energy level, there is neither loss nor gain of energy. Now, next. Next slide. Number 4. Postulate number 4 of the Bohr's atomic model. The emission or absorption of energy in the form of radiation can only take place when an electron jumps from one stationary orbit. So, if there is a nucleus, around the nucleus there are shells or the orbits, So, if an electron is jumping up over here or an electron is jumping down over here. If an electron is jumping up, it needs energy. It takes energy and goes up high energy level. If an electron is over here in high energy level, it jumps down by giving out energy. So, remember number 4, point number 4. The emission or absorption of energy in the form of radiation can take place only when an electron jumps from one stationary orbit to another. So here under postulate number 4, remember delta E, energy absorbed or evolved, delta E is equal to E higher energy level minus E lower energy level, and this is equal to H nu, that is equal to Hc by lambda. So this is a very important formula to note down over here. Whenever there is transition of electrons from higher to lower or lower to higher, then only there is either emission or absorption of energy. Energy is absorbed, as I have told you. Energy is absorbed when the electron jumps from a inner orbit to outer orbit, and it is emitted when it moves from outer to an inner orbit. That is number 4. Number 5. Energy of electrons in atom is quantized. I have already mentioned in my previous slide over there. Energy of electron is always quantized. It means that they have certain definite values and not any value of their own. Okay, now if you look at the success of the Bohr's atomic model, it has to be discussed. The success of the Bohr's atomic model of an atom. This has to be discussed properly, because see, if there was no discussion of the Bohr's atomic model, then further developments in the atomic structure detailed study would not have been possible. So it is very important to understand the success of the Bohr's atomic model. Number 1, this Bohr's atomic theory, it provides stability to the atom. Number 2, energy of electrons in various orbits of hydrogen atom or hydrogen-like atoms. That means if you take either hydrogen atom or hydrogen-like atoms like He plus or Li plus 2, etc., the energy of the electrons in various orbits can be calculated by using a formula. En is equal to minus 2 pi square me4 z square divided by n square h square. This is a very important formula to remember. So I repeat once more. Energy of electrons in various orbits, in any orbit, that will depend on the value of n. Okay, nth orbit. Okay. Now, to find the energy of the electron in various orbits, we must know the value of m, the mass of the electron, the charge carried by the electron, okay, the Planck's constant h, the atomic number is there already. Okay, so then it is possible, value of pi is known to all of us. Okay, 22/7. So it is possible to calculate the energy of the electron. Let us do the calculation also. Okay, now so in that formula which I have just written down, energy of the electron minus 2.18 into 10 to the power of minus 18 that square divided by n square. The unit is joules per atom. Okay, now upon simplification we get roughly minus 1312 z square by n square kilojoules per mole. Okay, now there is a negative sign over here in this formula. Okay, there is a negative sign over here. Very important. Why negative sign? The negative sign shows that electron is under attraction towards nucleus. So this is a very important sentence to understand and remember. Okay, because in order to calculate the energy of electrons in various orbitals, we need to remember the formula. Okay, as I mentioned in the previous slide over there. Okay, there's the formula over here. Okay, so based on this formula, if you look further, put the relevant values over there for the various abbreviations, we get something like a figure like this: minus 1312 z square by n square kilojoules per mole. Okay, So there is a negative sign over here. So to understand this negative sign, keep in mind that the electron is under attraction towards nucleus because nucleus carries a positive charge, so it attracts the electrons. That is why we put a negative sign. Okay, that was number two. Then let us go to the next slide over there. Now, post number three, the discussion point number three. Radius of various orbits of hydrogen atom. Radius, I am talking about the radius. Radius of the various orbits of hydrogen atom. If I talk about hydrogen atom, or helium ion, or lithium ion, etc., can be calculated by the following formula. There is another formula to learn now. Radius is equal to n square h square by 4 pi square n e square z. This is very important formula to remember. To calculate the radius of hydrogen atom or hydrogen like atoms, helium or lithium ions, we have to remember this formula. If you substitute in this formula the values of mass of the electron, the charge carried by the electron, the Planck's constant, etc., etc., then the radius of the electron, radius of the atom comes out to be something like this. N square is there already, h is Planck's constant. If you put the value, given values, 529 into 10 to the power of minus 10, okay, that is divided by z over there. This is in meter, by the way. Okay, now upon further simplification, you can get n square into 0.529. You can put angstrom to remove this, okay, divided by z. That comes to n square 52.9 upon z picometer. Okay. So the radius of the first orbit of hydrogen atom, radius of the first orbit of hydrogen atom, it is coming roughly to 52.9 pm. Okay, this you remember. Please try to remember this value. Okay, and this value, it is called Bohrs radius. It is called Bohrs radius. It is called what? Bohrs radius. Okay, so this was discussion number 3. Then let us go to the next slide. Then we go to the fourth discussion, or fifth one, I believe. Atomic spectrum of hydrogen atom can be explained by this theory. Can be explained, correct. The atomic spectrum of hydrogen has been possibly explained by this Bohr's atomic theory. The last one, number 6 maybe. The velocity now, a very important. Electrons are never stationary. So the velocity of electron can be calculated for hydrogen atoms. For hydrogen atoms, you can calculate, or hydrogen like atoms, if I talk about helium ion or lithium ion, by using the formula. Again, there is one more formula. V stands for the velocity, 2.19 into 10 to the power of 6 z over here, okay, atomic number by n. That is answer, unit is meter per second. So the velocity of electron can be calculated for hydrogen like atoms or hydrogen helium ion or lithium ion by using this formula. So try to keep this formula also in your mind. Okay, now this was the success story of the Bohr's atomic model, but the sad thing about the story is there are limitations as well. There are limitations as well to be understood and remembered. Why the Bohr's atomic theory was not a success at the end of the day? Let us do one by one. First one. This Bohr's atomic model does not explain the spectra. Remember this, spectra of multi-electron atoms. Multi-electron atoms. It does not explain the spectra of multi-electron atoms. That is first limitation. Also, it does not explain the fine spectra. Does not explain what? Fine spectra. Does not explain the fine spectra of even hydrogen atoms. Fine spectra of, we can say, hydrogen atoms. Okay, that is the second limitation. Then the third limitation of Bohr's atomic model, let us see. It does not explain the splitting of spectral line. It does not explain what? Does not explain the splitting of spectral lines where in magnetic field in magnetic field. It doesn't explain the what they call splitting of spectral lines in magnetic field. Whenever a magnetic field is brought close to the spectral lines which are formed on a screen, and then there is splitting of those spectral lines. And sad to say, the Bohr's atomic theory could not explain this splitting. This splitting of spectral lines in magnetic field is called, it has been named after, Zeeman. Don't say Amen. It is called Zeeman effect. It is called Zeeman effect. And also at the same time, the splitting of spectral lines in electric field, in electric field, in electric field also could not be explained by this theory. And this splitting of spectral lines in electric field, it is called Stark. It is called Stark effect. So you must remember these words over here. Splitting of spectral lines in magnetic field is called Zeeman effect. Okay. And the splitting of spectral lines in electric field is called Stark effect. So that is very important. This is, you will get half marks question or 1 marks question from here. The next limitation, number 4. This theory is not in agreement with de Broglie's concept. It does not agree with de Broglie's concept and Heisen's uncertainty principle. Two things to remember. It does not agree with de Broglie's concept. I'll come in detail to the de Broglie concept later in this chapter. And does not agree with Heisenberg's uncertainty principle. Okay. The last over limitation number 5. Bohr's theory also does not explain the three-dimensional structure of atom. So these are the limitations which you must remember, okay, and keep in mind. Now the reason why the Bohr's atomic structure of atom was not successful. Okay. Now the next thing I'll be discussing will be the most important part of this chapter, which is called quantum mechanical model of the atom. Now let us discuss the quantum mechanical model of the atom. According to this quantum mechanical model of the atom, this is a new branch of science, okay, which is based on dual nature of matter and Heisenberg's uncertainty principle, okay. And this branch of science, which deals with both dual behavior of matter and Heisenberg's uncertainty principle, is called quantum mechanics or wave mechanics. And this quantum mechanical model has been able to overcome the defects, the limitations of the Bohr's atomic model. Now here it is important to understand the dual behavior of matter, which has been explained by de Broglie. Dual behavior of matter. Which has been explained by whom? By de Broglie. Okay. Now, according to this de Broglie statement, all the material particles such as electrons, protons, neutron, atom, molecule, a ball, etc., in motion exhibit wave nature as well as particle character. So, that is an important point. Wave nature as well as particle character. Okay, so remember this. All the material particles, it can be electrons, protons, it can be electrons, it can be protons, it can be neutrons, it can be atoms, okay, it can be molecules, okay, it can be balls in motion, but they have to be in motion. They exhibit a dual nature. That is called de Broglie's concept over here. Now, light radiations also possess wave as well as particle nature. Very, very important point to understand. Light particles, light radiations also exhibit a dual nature, wave nature as well as particle nature. Okay. Now, light radiations showing the phenomenon of interference and diffraction explain the properties of wave, but photoelectric effects show the particle nature of light radiations. So, according to this person de Broglie, there is an equation given by him. De Broglie's equation. Now, de Broglie's equation, it has been given lambda is equal to h by mv, where m stands for the mass of the particle. Okay. So this same equation can be written in another form. Lambda is equal to h by p. Now this p stands for the momentum. Momentum, product of mass and velocity of the particle is momentum. You can also modify this equation. Lambda is equal to h by p is equal to h by this momentum can be written as root under 2 ek, that is m. Now here ek stands for the kinetic energy of the particles. Okay, kinetic energy of the electrons it can be. Okay, so depending upon this, we can modify the equation like this. H lambda is equal to h by root under 2qmv, 2qm capital V over here. Now please remember this q over here in this, it is the charge, charge carried by the electron, and capital V, this q is the charge, and the capital V, it is the potential of the electron. Okay. Now for this equation, if you know the value of the q, the m, and the Planck's constant, we get lambda, value of lambda, it comes roughly to 12.27 by root under capital V. Okay, there is so many angstroms. Okay. Now the next thing you must try to understand is, it is called Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Now, according to Heisenberg's uncertainty principle, it states that it is impossible to measure simultaneously the exact position and exact momentum of a moving particle like electron, proton, etc. I repeat once more. It is impossible to measure simultaneously the exact position and exact momentum, position and momentum at the same time of a moving particle like an electron. So, correspondingly, there is a relation over here, delta P, delta X greater than equal to h by 4 pi. Okay. Or this equation I can write it as mass of the particle is constant, so I can write this P stands for the momentum, remember, m into delta V, because delta V velocity varies, and delta X again greater than equal to h by 4 pi over here. A very, very important equation over here under Heisenberg's uncertainty principle. Okay, now delta X over here, delta X stands for what? In this equation, m delta V delta X, greater than equal to h by 4 pi. This delta x is called uncertainty. Uncertainty, uncertainty in the position, in the position of particle, that is delta x. The next one is delta p, that is again uncertainty in the momentum of particle. Then there is delta v. Delta v is called uncertainty in the velocity of particle. And lastly, over there, m is called mass of particle. So these are the abbreviations from the Heisenberg's uncertainty relationship over here. Okay. Now, please keep in mind, an electron cannot exist in the nucleus. That is a very important key fact to keep in mind. So, if an electron cannot exist in the nucleus, it has to be outside the nucleus. And when it is outside the nucleus, it is not stationary, it is always moving. That is why the question arises regarding the location, regarding the exact position and the exact momentum of the moving particle, like electrons or protons outside the nucleus. Okay. Now, after this Heisenberg's uncertainty principle came a very important equation under quantum mechanical model of the atom, which is studied under wave mechanics. It is studied under wave mechanics, and that equation is called Schrodinger. Schrodinger. It is called Schrodinger wave equation. Schrodinger wave equation, a very important equation. It comes under wave equation. Now this person Schrodinger developed a mathematical equation named after him, which describes the behavior of wave function associated with atomic particles. He considered the electrons as three-dimensional waves. This person considered electrons as three-dimensional waves, three-dimensional waves, three-dimensional waves in three dimensions. So, correspondingly, these three-dimensional waves, in electric field of the positively charged nucleus. So, what are electrons? Electrons are three-dimensional waves, according to Schrodinger, present in a positively charged nucleus field. So, the equation was given like this: del square psi del x square plus del square psi del y square plus del square psi del z square plus 8 pi square m by h square e minus v psi is equal to 0. This was the Schrodinger wave equation. Okay. Now, here in this Schrodinger wave equation, if you see, there is m, this m stands for the mass of the electron. It stands for the mass of electron. There is a alphabet over there, capital E. Capital E stands for total energy. Energy of what? Total energy of electron. Then capital V is there. V stands for potential energy of electron. Potential energy of electron, that is equal to minus z e square by r. Okay. Then there is small h, that is, of course, it is called Planck's constant, whose value is always given in the examination for calculation purpose. And small x, small y, small z, what are these? These are Cartesian coordinates. These are what? Cartesian coordinates. That means coordinates of the x plane, x plane, you can say y plane, and z plane, x and y and z plane. Okay. And this abbreviation psi, psi, a wave function which represents the amplitude, represents what? The amplitude of the electron. The symbol psi represents what? It is a wave function which represents what? The amplitude of the electron. Now, what is the significance of psi? Let us see. Significance of psi. That is very, very important to understand. Now, number one, psi represents the amplitude of wave and describes how this amplitude varies with distance and direction. Okay, this represents what? Amplitude of wave. Psi represents amplitude of wave and describes how this amplitude varies with distance and direction. Now, the second significance is quite awkward. It does not have any physical significance. Okay. Then, in that Schrodinger wave equation, you will see another alphabetical abbreviation. This is called psi square. So, significance of psi square needs to be understood over here in wave mechanics. Now, psi square gives what? Intensity. It gives intensity of electron. It gives intensity of electron. Okay. Also, the value of psi square is helpful in determining the probability of electron in a given region. Higher the value of psi square indicates greater probability of finding the electron. The zero value of psi square, if there is psi square value 0, the probability of finding the electron is also 0. Okay. Psi square is known as probability density. Psi square is also known as what? Probability. Density is known as probability density. Okay, and is always positive. Now, psi square also, describe the region of space around the nucleus where the probability of finding the electron is maximum. And this psi square is also called, according to wave mechanics, it is also called an orbital. So, my dear students, when this Schrodinger wave equation was solved, when this equation was solved, that led to the concept of what we understand today. Okay, the solution of this Schrodinger wave equation led to the establishment of numbers, very special numbers, which are called quantum numbers. And today, because of the mathematical solution of the Schrodinger wave equation, we have understood very nicely, very properly, what is an orbit, shell, subshell, and orbital. Okay, so orbit is well-defined circular path around the nucleus in which the electron revolves. It is circular in shape. It represents an electron, moves around the nucleus in one plane, all those things. Subshells are represented by here. Orbits, as I have told you, orbits, you have heard this in lower classes, K, L, M, N, corresponding to 1, 2, 3, and so on. Okay. When we talk about subshells, then we have alphabets S, P, D, F, etc., which have 2, 6, 10, 14 electrons respectively. Okay, these are subshells, you can see. And then there is a concept of orbital. Orbital is nothing, it is nothing but a region in three-dimensional space around the nucleus where the probability of finding the electron is maximum. So please keep in mind, S orbital, there is only one orbital. Okay, P orbital has 3 subshells, D orbital has 5 subshells, F orbital has 7 subshells. So S orbital, how many subshells? one subshell. Okay. P orbital has three subshells. D orbital has five subshells. F orbital has seven subshells. So try to understand. S orbital. An orbital can accommodate how many electrons? Two electrons. See. P orbital three subshells. So I'll draw three subshells like this. Three orbitals like this. 1, 2, 3. Each orbital two electrons like this. So there are 2, 4, 6 electrons. A p subshell, or we can say a p subshell orbital can accommodate 6 electrons. S orbital can accommodate 2 electrons. Okay, and D subshell, if you look at D subshell, there are 5 of them. 5 orbitals, 1, 2, 3, 4 and 5. Okay, so we put the electron 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons which can be accommodated in the D orbital. So this is one concept which have come after the Schrodinger equation was mathematically solved, which led to much more defined concept which is called quantum numbers. Now I will be discussing about the quantum numbers. Quantum numbers. Quantum numbers. Now, what are quantum numbers? The quantum numbers may be defined as a set of 4 identification numbers. These are nothing but numbers which are used to identify, which gives complete information about the electron in an atom. That is to know about the location. So quantum numbers help us know what? Know the location of an electron. It helps us know the energy possessed by the electron. The quantum numbers helps us know the shape of the electron. It helps us know the orientation of the electron. It helps us know about the spin character of the electron. So many information is provided by the quantum numbers: location, energy, shape, orientation, and spin. Okay. Now, the first quantum number. Now, let me tell you, my dear students, the quantum numbers are an outcome of the solution of the Schrodinger wave equation. So, because the Schrodinger wave equation was solved mathematically, that led to the obtainment of the quantum number concept, okay, which are called as principal quantum number, azimuthal or subsidiary quantum number, magnetic or orbital quantum number, spin quantum number, and etc. etc. And based after that, we came and derived the orbitals: s orbitals, p orbitals, d orbitals, and f orbitals. Okay. So now we shall learn about the quantum numbers one by one. Okay. Now let us see. The important quantum numbers are: number one. The first one is principal principal quantum number. Quantum number represented by small n. The second one, it is called azimuthal. Azimuthal or subsidiary quantum number represented by L, small l. The third one is magnetic or orbital quantum number represented by M, or we also write it as sometimes ML. Basically it is M. The fourth quantum number, it is called spin quantum number. Spin quantum number. Spin quantum number represented by, you can write small s. So These are the four quantum numbers. The first one is principal quantum number, then we have the azimuthal or subsidiary quantum number, then magnetic or orbital quantum number, and spin quantum number. Now the detailed explanation of these quantum numbers I shall do in my last video, okay, in the next video lesson class, okay. But let me briefly tell you a little bit about these quantum numbers. The principal quantum number, the first one, it describes the average distance of the electron from the nucleus. Higher the value of n, higher the value of n, this n, no? Higher the value of n, greater is the distance of the shell from the nucleus. Okay, so that is the important information provided by the principal quantum number. So you have to remember a formula over here, 2n square, which I will be discussing later on again. The next quantum number is called azimuthal or subsidiary quantum number, represented by symbol L. This describes the spatial distribution of electron cloud and the angular momentum of the electron. A very important thing to understand. I'll give you the formula later on about the angular momentum of the electron. So remember, the azimuthal quantum number or subsidiary quantum number describes the spatial, in space, the distribution of electron cloud in space, as well as the angular momentum of the electron, depending on the value of n. The third quantum number is called magnetic or orbital quantum number, represented by m. Now this explains the Zeeman effect. Now, what happens to electronic radiations when they pass in electric field, magnetic field, that is Zeeman effect. I have already discussed in this video quite some time ago. Okay, this magnetic quantum number, it explains the Zeeman effect. Magnetic quantum number determines the number of orbitals in a subshell. So how many orbitals are there in a subshell is determined by this magnetic quantum number. And finally, the spin quantum number, it tells us the direction of spin of the electron, whether the spin is clockwise or the spin is anti-clockwise of the electrons in an orbital. Clockwise, anti-clockwise, half arrow, clockwise, anti-clockwise, half arrow. So that is the spin of the electron system. So the spin quantum number denotes or helps us know about the spin of the electron, which may be either clockwise or anti-clockwise. So for spin we put a plus sign, we write plus half. For clockwise, for anti-clockwise we put minus half. So these are the brief information about the four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Okay, my dear students, I would like to end my class over here for today. In my next class, video class on this chapter, structure of atom, I will be doing in detail the principal quantum number, the permissible value of Ln subshell, all those notations I will teach you using what we call NLMS, various combination for various orbitals, and then I'll be teaching about the shape of orbitals, s orbital, p orbital, d orbital. I'll be teaching you about Pauli's exclusion principle in my next video lesson number 5. I'll be teaching you Bohr principle, how to write the electronic configuration, in terms of s, p, d, and f orbitals, and then finally, to end the chapter, I'll be doing with you the Hund's rule of maximum multiplicity in my next video. Thank you so much. Have a good day.